Next speaker would give her presentation online, but she'll show up for virtual Q&A. So our next speaker is Zuzana JELČICOOVÁ. So she is currently a PhD candidate at the Technical University of Denmark. Her research focus is neural network in resource-constrained hearing aids, while co-optimizing the software and hardware.
Hello everyone, my name is Zuzana JELČICOOVÁ, and unfortunately, as you can see, I cannot be present at the tinyML Research Symposium in person. However, please feel free to reach out if you're interested in our research. I'll be happy to discuss it with you. Today, I'm going to present our work called Delta Keyword Transformer, Bringing Transformers to the Edge through Dynamically Pruned Multi-Head Self-Attention. Firstly, we'll have a look at transformers and the key self-attention component that gives transformers powerful capabilities, but at the same time introduces an efficiency bottleneck. We'll continue by a quick overview of the existing research tackling this issue. Thereafter, I'll describe the original keyword transformer model that serves as our baseline architecture. I will also provide the analysis of the model on a keyword spotting task that served as a motivation to use the delta pruning method, which constitutes the core of our delta transformer. Finally, we'll go through the results, where the evaluations are based on the accuracy and computational costs in terms of multiply accumulates, followed by the conclusion. So let's firstly begin with transformers. Transformer neural networks have already achieved state-of-the-art results in many different areas, such as natural language processing, computer vision, and speech recognition. Their success lies in the multi-head self-attention, which is a collection of attention mechanisms executed in parallel. An attention mechanism can be described as mapping a query and a set of key-value pairs to an output, where the query, keys, and values are obtained by multiplying the input x with the projection matrices WQ, K, and V, as shown in equation 1. The matrices are then divided into k attention heads to perform the self-attention computations in parallel, with each of the heads defined by equation 2, where dh in the denominator is a scaling factor. Finally, all the attention heads are concatenated and weighted by another projection matrix, WP. Although self-attention is powerful, it becomes expensive as it requires multiplying two n times d matrices, which is n squared in time and space complexity, where n is the sequence length and d corresponds to the number of features within a vector in a sequence that is called a token. Therefore, large size and computational complexity that grows quadratically with respect to the sequence length becomes a bottleneck, making deployment of transformers to resource-constrained devices extremely challenging. Several works have already tried to mitigate this issue by proposing different techniques for multi-head self-attention pruning. These mainly aim for reducing the number of attention heads in each transformer layer and token pruning. Eliminating attention heads completely to speed up the processing might significantly impact accuracy. Therefore, token pruning represents a more suitable approach, where attention heads are preserved and only unnecessary tokens within the individual heads are removed. However, most of the listed methods focus on coarse-grained pruning or require demanding training procedures. We, however, push pruning to finer granularity, where individual features within tokens are discarded at runtime using a threshold in the multi-head self-attention pipeline. Moreover, our method does not require any training and can therefore be used directly in the existing pre-trained transformer models. Our motivation to apply threshold-based pruning is a result of an analysis that we performed on the original keyword transformer model, further called KWT, which serves as a baseline architecture for our delta keyword transformer. The KWT is a typical transformer encoder that consists of a stack of identical transformer blocks, in this case 12, where an output of one block is fed as an input to a consecutive block. Each transformer block comprises of multi-head self-attention, multi-layer perceptron, layer normalizations, and residual connections. The KWT takes as an input the MFCC spectrogram that is mapped to a higher dimension D using a linear projection matrix along the frequency dimension, resulting in T tokens with D features. These are then concatenated with a learnable class embedding token, XCE, that represents a global feature for the spectrogram. Subsequently, a learnable positional embedding XPE is added to form a final input to the transformer encoder. Thereafter, the steps to compute self-attention that we already described previously are executed. Residual connection is then added to the multi-head self-attention output and passed through the first layer normalization and the MLP block, followed by another addition of a residual input and second normalization. In the KWT model, the MLP block is a two-layer feed-forward neural network using a Gaussian error linear unit activation function after the first layer. The class embedding vector is extracted from the output of the last transformer block to perform classification. However, as all tokens attend to each other, a certain level of redundancy is expected to be found in the system due to diffusion of information. We analyzed the KWT model on the Google Speech Command dataset to observe the degree of change across the tokens as they pass through the multi-head self-attention. While considerable correlation across the tokens is expected for the initial input and intermediate results in the first layer, it's noteworthy to observe such behavior also in the multi-head self-attention of deeper layers. The first figure illustrates correlation between X inputs on the top, along with the difference between subsequent rows of this tensor at the bottom for the seventh layer of a keyword right. The second figure repeats the same analysis for the softmax output of layer 7. It's clear that there is a significant amount of correlation between consecutive tokens, which opens up opportunities for data compression and computational data reuse. Such a tendency was observed for all voice-containing input sequences. Moreover, when analyzing intermediate tensors from inputs of the silence class, represented by the third figure, even larger data redundancy can be observed. Therefore, fully computing every single token would be a waste of computational and memory resources. Hence, introducing a threshold for recomputing could drastically decrease the computational load and inference time, and also offer data compression. Therefore, we propose a delta algorithm that utilizes a threshold to discard insignificant values. The objective of the delta algorithm is to transform a dense matrix vector multiplication into a highly sparse matrix vector multiplication to reduce computational complexity and enable intermediate data compression. The reduction is based on the comparison of similarities between corresponding features of subsequent tokens, where only the above threshold delta differences are stored and used for computations. The idea of threshold-based pruning has already been explored for other types of neural networks, such as recurrent and convolutional ones. However, incorporating a delta threshold in these networks results in significant memory overhead, as it requires storing intermediate states and activations. This issue is eliminated in our delta transformer, where almost no additional resources are required. Let's now have a look at details of the delta algorithm. As described previously, the input X always starts with the class embedding vector, followed by the first input vector. These two vectors will always be left untouched throughout the complete multi-head self-attention pipeline. Every subsequent token after this will be represented by its delta value. This delta change, denoted as delta x in the equations, is calculated as the difference between the current input x and reference vector x hat. Only delta differences larger than a threshold theta are retained and used to update the reference vector x hat. The following figure visualizes the delta encoding over 3 tokens with threshold equal to 1. The top row represents the first input vector that is left untouched. Therefore, all vector values will be used as deltas, which is shown by blue color. All the values will also be set as a new reference for x hat indicated with the arrows. In the next time step, we start applying the delta algorithm. As it can be seen, only one absolute value of subtraction is greater than the given threshold. Hence, only this single value will be used for computations, while the rest will be skipped, denoted with zeros. Also, only a single value is updated in the reference vector, while the rest is kept from the previous time step. The same approach is then applied in the subsequent time step. We apply the delta encoding of data at 6 different places in the multi-head self-attention: layer input X, matrices K and Q, scaled QK transposed, softmax output, and the attention head output. While the computations of delta values are the same everywhere, the subsequent operations with these deltas differ depending on whether a delta encoded matrix is multiplied with a regular matrix, 2 delta encoded matrices are multiplied together, or a nonlinear softmax function is applied. The first version, called delta regular matrix multiplication, multiplies delta X with a weight matrix W as visualized in the figure. The output R of the tensor operation can hence be computed by accumulating the result of the previous reference token with the multiplication results of the weights with the delta values. The updated R will then be the new baseline for the upcoming token. These delta multiplications are used in layer input X, softmax output, and the attention head output. The second version is called delta-delta matrix multiplication, where both Q and K are expressed in their delta formats. Hence, the multiplications will be slightly modified. This is illustrated in the figure and expressed in a general form with matrices A and B, representing Q and K transposed matrices, respectively. The multiplication of the first A row with the first B column is done as usually without using deltas. Then, the multiplication of the first A row and second B column exploits the delta approach in horizontal direction, where the expressions highlighted with the red rectangles can be replaced with R00 from the equation above. The same approach is adopted in the vertical direction, now for the rows of A and first column of B. An approach for multiplications for all the other positions is demonstrated on the second A row and second B column, where different colors mark each of the three multiplications. The expressions not involving any deltas can be substituted with R00. Next, the terms with delta B are replaced with R01, while those containing delta A with R10. Since R00, R01, and R10 have already been computed in previous time steps, we only need to do the sparse delta multiplications themselves and subtract the R00 result as it is present in both R01 and R10. These steps are then applied to all the other slots in the result matrix. The last, third version of the delta algorithm is for the softmax function, as the original delta algorithm cannot be applied directly due to the nonlinearity. Therefore, we introduce a scaling factor to correct the softmax computations. As done earlier, we will again start by performing unaltered processing of the initial row R0 with a regular softmax function, while the next row is already expressed with deltas. Hence, the R1 nominator and denominator for softmax can also be expressed using deltas. Finally, by substituting the original softmax terms with a new nominator and denominator produces a scaling factor for each of the token values. All these three versions of the delta algorithm are applied in the KWT model, thus creating the delta KWT. 3 KWT models are proposed in the original work, where we selected KWT3 for our experiments, as it poses the biggest challenge as well as potential for compressing and reducing the computational complexity. The KWT3 configuration is listed in the table, and the places using the delta thresholds are highlighted in the figure. The results of applying our delta KWT on the keyword spotting task can be seen in the next slide. Our method, as well as the original KWT performance, were evaluated by classifying 4,800 Google Speech Command dataset keywords into 12 categories. While the thresholds might be different for each delta encoding within the multi-head self-attention block, they are the same across every transformer layer. We executed threshold sweeps and selected the configurations resulting in a Pareto optimal accuracy computations trade-off, focusing on the configurations that yielded at least 94% accuracy. These can be seen in the plot along with their delta configurations provided in the legend. The X and the left Y-axis show a percentage of executed max averaged across the layers and achieved accuracy, respectively. The second Y-axis represents a speedup factor derived from the amount of max. The blue circle corresponds to the original KWT3 model that achieves approximately 98.4% accuracy with 100% max. The red and green triangles represent our delta KWT3 model with regard to accuracy and speedup, respectively. The inference time gains for the multi-head self-attention range from approximately 1.05 up to 16 times, and there is no accuracy degradation down to approximately 24% of max, corresponding to a speedup of 4.2. If the accuracy requirements can be relaxed by 1 to 4%, the multi-head self-attention inference becomes faster by 7 to approximately 16 times, which translates to 87 to 94% of skipped max. The following table shows an example of the percentage of executed multi-head self-attention operations for one instance of each keyword category averaged across the layers. The configuration used to obtain the results is represented with a square in the plot. We can observe that up to 70 to 77% of max in total can be skipped in the model without compromising the accuracy. To further visualize the savings, the following figure shows the original input data X of the 7th layer of a keyword right from the table, and its delta values after applying our algorithm, where black color marks zeros. Likewise, the second set of figures shows the original softmax output and its delta version. One special case are the instances from the silence class, for which only a small fraction of the deltas is non-zero, resulting in 97 to 99.9% of skipped operations. Finally, let me now sum up what we have gone through in this presentation. I introduced a dynamic threshold-based pruning technique that drastically reduces MEC operations during inference. It was demonstrated on a keyword spotting task on the Google Speech Command dataset, where approximately 80% of operations into multi-head self-attention can be discarded without degrading the accuracy. If accuracy requirements can be slightly relaxed, a speed-up factor of approximately 7 to 16 times is achieved. Our method thus helps to considerably decrease the computational complexity and enable significant data compression. The proposed technique can be exploited to enable an ultra-low power wake-up word detection front-end that triggers a more powerful detector once a keyword is recognized. More generally, this work represents a stepping stone towards enabling the execution of transformers on low-power devices. These last slides conclude my presentation, and I would like to say thank you for your attention and for attending this session.
So maybe I can kick off the question. Zuzana, thank you for the nice presentation. You mentioned data. So I wonder across different data sets, so how consistent is the data? Do you adopt one empirical refined value for theta, or for different model and data set you would find different value of theta?
You are referring to the threshold that is applied
Yes.
on the data, right? Actually, the threshold is same for all the multi-head like self-attention modules that are within the transformer neural network. So it's actually applied on all the keywords. So it's the same for every single keyword.
I see. Thank you. So for transformer, despite the quadratic complexity, so if we look at the overall model, not necessarily the multi-head attention would dominate. For example, MLP might dominate in some scenario. In your setting, have you observed so the complexity ratio between the MLP and the multi-head attention?
Yes, that's a really good question. So we were looking actually at the distribution of complexity between the multi-head self-attention and the multi-layer perceptron. And actually in this case, it is the way you said, it means that the multi-layer perceptron, like this part of the neural network, is actually more dominant than the multi-head self-attention. However, since there have been already a lot of research that was about basically pruning and simplifying the multi-layer perceptron neural networks, then this was basically out of our scope. So we were really focusing on the multi-head self-attention. And we are also, like in our paper, referring to some of these techniques that were focusing on the MLP part of the transformer neural networks. So for us, it was this multi-head self-attention that was the most important part of the network to be pruned.
Great. Thank you for sharing. I think we have one audience want to ask question.
Yeah, so the delta encoding technique is really interesting. Did you consider any other encoding systems? There's lots of ways to encode matrices in sparse ways. And yeah, great talk.
Thanks a lot. Well, regarding the weights, like we were not focusing on the weights in this case, so we were trying to really capture the like the connection between our input. So basically how much the input has changed from the previous time step. But in general, we were also trying to use other encoding methods or basically other approaches. One of them is a deterministic approach where we were not using like an explicit delta threshold, but we were basically, so to say, letting the algorithm to decide what elements will be selected. And this will be based on the fact that we would only define the number of elements or number of features that we want to process within the token, and then based on that the algorithm would actually find the top elements that should be actually used for multiplications. So this was another way of encoding that we've tried to also apply on the transformer neural networks.
Thank you.
Yeah,
Thank you.
Thank you.
Yeah, so thank you, Zuzana, for joining us for the virtual Q&A, and thank you for your great work.
Yeah, thank you very much for having me.
And we are very thankful for our sponsors. The premier sponsor this year is Edge and Pulse. And then executive sponsors are ARM, DeepLight, Qualcomm, and Sentient. Platinum sponsor, Analog Devices, BrainChip, Infineon, Clickertech, Latent AI. NXP, Reality AI, Renaissance, Sony Semiconductor, and Synaptics. Really very diverse company, great companies who are really driving tinyML forward. Gold sponsors for the Hub, Micro AI, Prophecy, Seed Studio, SenseML, ST Microelectronics, SynSense, XMOS. And we have a list of civil sponsors: Avion Devices, Aspinity, Seva, EMSA, Greenwave Technologies, Gravity, Hymix, HOTG, Imagimob, Itemis, Lattice, Nota, OmniML, PixArt, Plumerai, Kixo, Rachner, Rixen, SAP, StreamAnalyze, Texel, and Google. So we are very thankful for their support, and more importantly, for them being part of this community and driving it forward.